So in this lecture, I want to talk about modified Pascoaletti-Serafini. So instead of SP of A and R, we are talking about P bar of A and R. And so instead of saying is inside the cone, we say it is equality and is equal to the vector 0. And so the relationship between Pascoaletti-Serafini SP and SP bar is like this. The theorem is like this. That if X bar is a minimal solution of a scalar optimization problem, then there is a K bar such that this is satisfied. And there is a parameter A prime that it is equal to 0. I mean, the vector of 0. And so we are using, so geometrically, this is a reference point when we have 0, and this is when we are doing it in a non-trivial case. And here we say that the hyperplane be given and X bar is in the minimal set. And then there is a parameter A and T bar, so that T bar is also a solution of SP bar. SP, and so this is a simple problem. So let's recapitulate the Lagrange multiplier. Let's make a summary. Okay, so we define Lagrange multiplier at point X if it satisfies these conditions. Why is it important? Because we know that the minimum and maximum of an optimization problem satisfies, at least the necessary conditions of the KAT condition is that the derivative of the Lagrangian is equal to 0. And that's why all of the points should be greater than equal to 0 if it is if the inner product between the gradient of Lagrangian with respect to x and the vector is greater than 0. And we can say that so these are the Lagrange multiplier. Mu and Kc are the Lagrange multipliers, and G is here, and H is the equality constraints. G just belonging to that, and the theorem says that mu, nu, and Kc are also Lagrange multipliers to the points. We can prove it easily, like this. So we are interested in sensitivity of the scalarization because we want to say that, for example, if A is on the hyperplane, what is the next A? If A1, A2, A3, all of them belong to this hyperplane, when we calculate one of them, find one of them, we want to find what is the next step, what is the next A, such that if all of them goes to the objective space, that we have some efficient frontiers, minimal points here on the efficient line, then we want them to be equidistant. The distance between this one and this one, the distance between these points on the efficient frontier, we want to have same equidistance and become alpha. And to prove that, we try to make to prove some theorems that are needed. For example, the local value minimum function is, we define this one So the minimum, the infimum of all t such that it belongs to a ball. So if we found, for example, one point x bar, which is efficient, which is a minimal point, and corresponds to t0 as well. So this point, we want to make a ball around it with radius delta, such that we want to see how, in which direction should we go for that if we evaluate that on the objective space. So this is the objective space, and these points are on the efficient frontier and are minimal. So we want to see in which direction should we go that has highest sensitivity. For example, in this direction, you can see that the difference between them, we want to be alpha equidistance. And also, so our second target is that we want to prove because all of them are inside the hyperplane, which is generated by some bases. And we want to, first of all, say that in which direction on this hyperplane we should move to find another reference point, A. So that A plus TR minus f of x belongs to the cone K. So we approximate the local minimum function, and we can determine further approximations. So we control the distance between the minimal points, which we fix to alpha. And so we need to know about Frechet derivative. I mean, this generalization of derivative for example, if we can find a t, if there exists some t is it's a linear operator from v to w, so it goes from v to w, and for example, if your function f is from r to r, then it's simple derivative and they coincide. Of course, there are even more generalized definitions for derivative. Getex, the French mathematician, like Frechet, but both of them, I mean, both the Getex and Frechet derivative, they coincide if it is differentiable. If f is differentiable, both of these definitions, they coincide. So I said that if f is differentiable, then it's the simple gradient function that we always use. And we need to know that this is a long theorem that says if this minimization problem has these assumptions as well as this assumption, then we can say that the Lagrangian multiplier, I mean mu I and Kisui I, are unique and satisfy this inequality. And of course, the point of this theorem is that we are trying to approximate the derivative of that value function that I was talking about with derivative of Lagrangian with respect to a parameter that we will use it. And the proof is based on implicit function theorem. It's so interesting because if you have some graph of a function, some graph like this, for example, f of x and y is equal to 0, then you can somehow relate those terms. So you can relate the independent variable x to a dependent variable y. So this theorem has used this proof. You know, the implicit function theorem and all of them are really important, because our problem is a geometrical problem. So you need to be familiar with geometry of manifolds, that in a global a geometry, if we are looking at it as a global perspective, if we have for example, n-dimensional manifold, we try to find some charts that locally, like this, locally you can define it by some approximation and find the tangent plane which is attached to the manifold, so that you can approximate it. And this is the whole thing about these implicit function theorem that is used in geometry of manifolds very much. And recalling from the modified SP, I said modified because it is not longer an inclusion, but it is just in equality, and so it is equal to 0. And we can say that we can find the sensitivity of the problem. Also, we need to know about the Hessian of the Lagrangian, which is if we define W by this, and this is the Hessian of the Lagrangian. It is useful because in KKT conditions, that is a generalization of the Lagrange multiplier, because we are adding the inequality as well. Although we have some necessary conditions, all of them are necessary conditions, but sometimes we need to know the sufficient condition as well, and so it should satisfy this as well. And we will see that this, how it is shown in the theorem here. It's like this. So this is the typo error in this book. So this is for the whole vector. And so this one, the whole thing is just a scalar, which is greater than this number. And you will see the point that the lemma tries to say, that it says that assume there exists an alpha tilde such that this holds, then there is a constant alpha such that this one holds. And we need this for a proof of a theorem that says that if we consider the parameter dependent problem, the modified Pascoletti-Serafini, we can say that these are the assumptions of the theorem. And finally, we can say that there exists a delta such that your local minimal function is differentiable, and it has a derivative as well. And the derivative is the gradient of Lagrangian with respect to A and R. We use this in our adaptive approach to find in the proof of saying that we have a hyperplane and we have an A. We have solved the equation, the Lagrangian and all of them. We have found the Lagrangian multipliers, and you want to find the next A, A tilde, for example, such that if they go through the objective space on the efficient frontier, the distance between these 2 points on the efficient frontier becomes a fixed number. So any 2 points on the efficient frontier, for example, this one and this one, have the equidistance, and the distance is alpha. And so we need this. We need to know what is the gradient of this value function, that in order to prove that. So the derivative of the local minima is this one, and we can assume if you just use C as trivial cone for C, then then the gradient, the sensitivity, is just an easy vector. And for the first order approximation of your value function, we can use first order Taylor approximation like this. And I will explain in the next lecture how we are trying to relate the T and F such that we find equidistance on the objective space. So, for example, if this point and this point and this point, if these points are on the objective space, are on the efficient frontier, then the distance between them is alpha. The distance between them is alpha. So you need to find a hyperplane, for example, in three-dimensional or any dimension, such that if you just put the point A inside that, it goes to some, you find the A, it goes to some point on the efficient frontier, such that the distance between these efficient frontier points, these minimal points, is constant, and it is alpha. So I will explain it in the next lecture.